now that we have the chain rule, we can talk about a thing called a directional derivative in a nice way. And we've already seen directional derivatives for particular directions. That is, if I have, for example, a function f of x1, x2, and I have a line x of t is equal to t comma 0, and I compose this, then I have f of x of t comma 0 is equal to f of t comma 0. And if I take a derivative of this function with respect to d, df dt, we'll say f sub 0, and that means that I've set the second thing equal to 0 and evaluated at t. Well, that's just going to be the partial derivative of f with respect to x1, because all I'm doing here is changing x1 and I'm leaving x2 to be fixed at 0, evaluated at t 0. So this is actually a directional derivative, and we've already seen it, and we can do it in all the other coordinates as well. Now this suggests that I can plug in a general direction. And what do I mean by a general direction? Well, I mean I plug in a general parameterized line, which is also a parameterized curve. It's a very nice parameterized curve. And what does it look like? Well, I have x naught plus tv, where v is some direction that I'm taking. And v can be anything in my space, and x naught can be anything in my space. And what do I get when I compose this function, right? Well, this is essentially a function from R1 into Rn. And generally I have a function f from Rn into R1. So when I have this particular f of t, I have f of x naught plus tv is now a function from R1 into R1, which means I can take a derivative and I can employ the chain rule. That's great. So let's get an example. Something relatively simple. F of x1, x2 is equal to 4 minus x1 squared minus x2 squared. And we're just going to look at this guy in the positive orthont in these many dimensions. So this will be 4, say this will be 2, this will be 2. And of course this function is the parabolic hill that we've been looking at. This is a nice simple function, is why I keep bringing it up, and it really illustrates a lot of the underlying behavior here. And we're going to be interested in the point 1, 1. Right there, that's my point. Very good. And let's say I want to take a directional derivative, and I want to take it in the derivative. So normally I've taken a directional derivative, and I can compute the derivative along the line where I keep y is equal to 1, and I vary x, and I can take a derivative along this line. But now I want to do something a little more interesting, and take the derivative along the direction of this line. So now I just need a parameterization of that line. But be careful, because every parameterization is going to give you actually different derivative, right? So that, just keep that in mind. Well, and I want to take the derivative at this point, so I'm going to set x naught equal to 1, 1. And I'm going to say v is equal to 1, 1. Then what is my derivative? Well, df of x, or df composed with x, so that little circle means composed, dt, evaluated at time is equal to 0 of this curve. So my curve now is x arrow is this thing where now I've fixed x on and v. Well, that's equal to df dx1 of 1, 1. And what's the derivative of this guy? with respect to t. That is the first coordinate, right? So this should be dx1 over dt of 0 plus df dx2 of 1, 1, dx2 dt of 0. Well, right, this curve is exactly x of t is equal to x naught, which is 1, 1, plus t times 1, 1, which is equal to 1 plus t, and another 1 plus t, which is great. And I know the derivatives of each of these particular functions. The derivative of this thing with respect to t is 1. The derivative of this thing is with respect to t is 1. So I know that this term is 1. And I know the derivative of this thing applied at 1, 1 is going to be, well, the partial of this will be negative 2 times x1. So I get negative 2 times 1 at x1 is equal to 1. So I get negative 2 here times 1 plus negative 2 times 1, which in the long run gives me negative 4. And that gives me the derivative at this point, and it tells me I can compute a tangent line along this direction, and that gives me the slope in the xy, and in the z direction, right? So this will be x1, x2, and f of x1, x2, sometimes called z because we can. So we've seen a nice example of one particular directional derivative, and they're pretty simple to compute as long as we have that line. In general, we have, and you can verify this, we have a particular line, x of t is equal to x1 naught, x2 naught, up to xn naught, plus t times my direction, and I'm going to have df dx1 at x naught all the way up to df dxn evaluated x naught, and I'm going to multiply this by v1 to vn. If you notice, this is exactly the directional derivative. This term, multiply this by this, you get a scalar, and that's the directional derivative. And we set this equal to, symbolically, df at x naught dotted with v. So this is a vector, right? If I put all the partial derivatives at a particular point together in a row, then I have a vector, which I'll call the derivative of f at x naught. And then if I have a direction that I'm taking a derivative along, then I get v1 up to vn, and that is my v vector over here. And so this is the directional derivative at x naught in the direction v. Now you'll notice that this term is going to be the same no matter what direction I choose, right? If I fix my x naught, then this guy is going to look the same no matter how I change my direction. So I can choose a bunch of different directions over here to take derivatives along, but this will always be the same. This is an object we call the gradient, and we're going to talk about that in our next video.